All right, so we learned what the sine is. We've been playing with it for a few days. We learned what the cosine is. We've been playing with that with a few days. And now we have the tangent function. I'm going to show a new function called the secant. And my claim in this picture is that the secant of the angle in the unit circle here is going to be equal to the bars around this mean the length of the segment AE. So let's see, where is AE? A is down here. There's my A, and E is up here. So this length right there, my claim that is the secant. Now I also claim here that the tangent of the angle is equal to DE. Here's D over there. There's E up there. So my claim is that that length right there is the tangent. So I'm going to do a little trigonometry magic and check that out. So again, I believe this length is the secant of the angle. I'll define the secant another way in a second. And that this length right here is the tangent of the given angle, theta. So we started off playing around with trigonometry on the unit circle where the y value, which would be, oops, on a different color, the y value of that point is this length. That is the sine of the angle. So we already learned that on the unit circle. That y value is the length of that line. And the x value down here, which is the length of that part of the triangle right there, that is the cosine of the angle. The radius here, remember, our r is 1. So I have two triangles. I have this bigger triangle and I have this little triangle there. And so let's take a look at my big triangle and my little triangle. So I'm going to redraw over here the little triangle in green. It looks something like this, not quite to scale. Here's that angle theta. That's 1. That is the sine of theta, and that is the cosine of theta. And that is a right triangle. And then we have the bigger triangle here, which is the same shape, it's just a little bigger. How do I know it's the same shape? Well, it has this same angle theta here, and it has a right angle here, so that third angle has to match. So whatever this angle is, has to be the same as that angle up there. And my claim is that this side here, the vertical side, the measure of it is whatever the tangent of theta is. It's my theta, and that this long side here, the hypotenuse, is the secant of theta. Now, what's this side at the bottom here? Let's see, on the blue triangle, that side on the bottom is the radius. So this side down here has to be 1. Now, what I want to do is just play around with the idea of similar triangles, which hopefully you did in a past geometry class. And what similar triangles says, if you have two triangles that have the same shape, but not necessarily the same size, ratios of similar sides are equal. So for example, on this green triangle here, if I consider what's the ratio of the vertical components of that triangle to the horizontal component of that triangle, you would say that ratio is the sine of theta, right? The length of that side divided by the cosine of theta. So that would be on the smaller triangle. And on the bigger triangle, the ratio of the vertical to the horizontal would be equal to whatever the tangent of theta is divided by 1, right? So all this is just a property of similar triangles. Property of similar triangles. Triangles, there we go, slightly better. So ratios of similar sides have to be equal if the triangles have the same shape, and they do have the same shape because they have the same angles, right? We can see that. So the blue triangle here is just a blown up version of the yellow triangle or the green triangle. All right, now look at this, what I wrote here. Highlighter out. Dividing by 1 is lame, nothing happens. This says that the tangent is equal to the sine over the cosine. We knew that, that's true. Right, so I'm just proving my claim that that vertical length has to be the tangent when I extend that radius out past the circle. Next, let's look at my claim about the secant. To investigate the claim about the secant, the ratio I'm going to choose is the hypotenuse divided by the horizontal part. So I'm going to take, what is the ratio of the hypotenuse divided by the horizontal component of each of these triangles? And we'll do the small one first. The hypotenuse is 1, the horizontal is cosine. So the ratio on the small triangle is 1 over the cosine of theta. And on the bigger triangle, it would be the secant of theta divided by 1, right? I'm looking for what's the hypotenuse, that's the secant. And then the horizontal is 1, divided by 1. And I can clean that up a little bit. I'm going to put it up here at the top. If I clean it up a little bit, secant divided by 1 is just secant. So this tells me that the secant of theta, SEC, is equal to 1 over the cosine. And so this is one definition of that new function. So we looked at the tangent earlier. Now we have a new trigonometric function called the secant. Okay. Secant function is 1 over the cosine. Now remember, another way to think about a cosine on any circle, the cosine is always the x value over the radius. So another way I could define the secant is by saying, flip that, right? 1 over the cosine. It would have to be the radius divided by the x value. So those are two different ways to think about the secant. Super important relationship in trigonometry, another function we need to know. All right, so we're going to take this just a little bit farther. So reminder about what the sine means. It is the y value divided by the radius on any circle. The tangent is the y value divided by the x value. And now we know that the secant is the radius divided by the x value, which is the flip of the cosine, 1 over the cosine, the reciprocal of the cosine. Now, this picture I have drawn here actually tells me something even more cool. And actually, let's look at this version of the picture. I'm going to bring this into a new screen. And we talked about this last class. This is what's called the Pythagorean identity in trigonometry. Trigonometric. Pythagorean identity. Oops, Zoom is in the way. Identity. And let's bring in that picture. Yep. All right, so let's check this. Ooh. Check this picture out. So here I have a right triangle, true. And sometimes we call this length the cosine for doing trigonometry. Sometimes we could just call it x. And sometimes we call this the sine, but we could also call it just y. And the regular Pythagorean identity says that x squared plus y squared equals 1. Right? Now, x is really just the cosine. So this is the trigonometric version of it. So if I take, oops, wrong order, the cosine of theta, and then I square it, right? That's x squared. If I take the sine of theta, and then I square it, it has to be 1. Right? Pythagorean theorem says that if you square the lengths of the legs, and add them up, you get the square of the hypotenuse. 1 squared is just 1. So we went over that before, but I got a new one. Notice that we have another right triangle here. We can write an identity related to that one, related to the Pythagorean theorem. So let's steal that picture. Another, so back here, this one right here is, I would say we call it the trigonometric Pythagorean identity, right? This is the most important one. But there are other relationships that are sometimes important. And if I look at this one right here and apply the Pythagorean theorem to it, if I take this leg, tangent of theta, that's some measurement, right? I can plug in theta and get an answer. And I square it and I add it to the other leg, 1 squared, that has to equal the hypotenuse squared. That's what the Pythagorean theorem says in general. So this is another trigonometric Pythagorean identity. And as we move along in this course, identity, we're going to collect a lot of identities. We're going to have a couple pages of them by the time we're done. And I don't need you to memorize all of them, but I do need you to memorize a few of them. And I'll remind you of that regularly. So here's another identity. 1 squared is just 1. So I'm just going to get rid of the square there. So this one says that the tangent squared plus 1 squared is equal to secant squared for any angle that we pick, no matter what the angle is. So let's test that out here. Let's play with pi over 6 for a second. So I want to know what is the tangent of pi over 6. I want to know what's the secant of pi over 6. Okay, well, tangent, remember, is sine over cosine. So I can say, all right, instead, what is the sine of pi over 6 divided by the cosine of pi over 6? So then I envision in my head my unit circle. So I'm thinking that unit circle that I've asked you guys to memorize, and pi over 6 related degrees, 30 degrees. So that means I'm down here, pi over 6. And the x value there is bigger than the y value. Okay, so that right there must be the point square root of 3 over 2, comma 1/2, because I know square root of 3 over 2 is bigger than 1 over 2. So that's the point here, right? X is bigger than y at pi over 6. Let's see, x is the cosine. So that means the denominator here is the square root of 3 over 2, and the numerator is 1/2. The halves divide out, leaving just 1 over the square root of 3. So my claim is that the tangent of pi over 6 is 1 over the square root of 3, and I can confirm that on a calculator. Let's grab a calculator. Not there. I want that one. Oops, I'm in degree mode. Let's get rid of that. By degrees, we don't want degrees. Although you have a few homework problems in degrees, mostly I'm going to try to not assign any. Let's switch back to radian mode. Always pay attention to the mode of your calculator. And I want to know what is the tangent of pi over 6, right? And computer says it's 0.577-ish. And if I compare that to 1 over the square root of 3, it better be the same number. It is the same number. Okay, so my knowledge of the unit circle helped me get an exact answer on that. All right, secant. What's the secant? Recall we've defined the secant earlier. The secant is equal to 1 over whatever the cosine is, and they have to have the same angle. And I know that the cosine is square root of 3 over 2, and there's a 1 in the top. And when you divide fractions, the bottom one flips, so that would be 2 over the square root of 3. All right, so now what I want to check is, I said for any angle, doesn't matter what the angle is, this should be true up there. All right, so this says take the tangent, find the value at that angle. All right, so that's 1 over the square root of 3. So I'm just applying this right here. 1 over the square root of 3, and then I have to square it. Here I have a 1. Secant I just have found is 2 over the square root of 3, and then I got to square it, right? And these two things should be equal. Let's see. Let's see, if I square 1, I get 1. So let's go that way. And if I square the square root, I get 3. And then I have to add 1 to that. 1 would be 3/3. So 3 plus 1, this is 4/3 on the left. On the right side, I square 2 and I get 4. I square the square root and I get 3. And I can see, hey, they are equal. Yay. Got it. All right, moving along.